What is the fastest and slowest thing in the universe? Believe it or not, both extremes are happening all around you. Right now, while you sit listening to these words, convinced of your stillness, the atoms in your body vibrate trillions of times per second. Your cells divide in processes that take hours, while your neurons fire electrical signals in milliseconds. The chair you occupy hurtles through space at over 100,000 kilometers per hour as Earth orbits the Sun, yet you feel nothing. Simultaneously, particles deep within your body move at nearly the speed of light, while the expansion of space itself carries distant galaxies away from us at velocities that exceed light speed without violating any physical laws. This contradiction reveals a fundamental truth about our universe. Motion and stillness are not absolutes but relatives, dependent entirely on perspective, scale, and the frame of reference we choose to adopt. The story of speed spans from temperatures so cold that atoms would theoretically cease all thermal motion to cosmic phenomena where space itself expands faster than light can travel through it. But why should this matter to you? Understanding the extremes of motion unlocks profound insights into the nature of reality itself. Every technology you use, from the smartphone in your pocket to the GPS satellites overhead, depends on our mastery of these principles. The same physics that explains why absolute zero represents perfect stillness also explains how your computer processor can execute billions of operations per second. The relativity that governs black holes also keeps your satellite navigation accurate to within meters. More fundamentally, this journey through speed reveals the elegant unity underlying apparent chaos. The same quantum mechanics that makes chemical reactions crawl at near absolute zero also governs the nuclear fusion that powers stars. The gravitational effects that can slow time to a crawl near a black hole also determine the precise orbital mechanics that keep planets stable for billions of years. The electromagnetic waves that carry information at light speed also determine the chemical bonds that make life possible. This exploration will transform your understanding of familiar concepts. You will discover that the solid matter you trust is mostly empty space filled with particles in constant motion. You will learn that time itself is not the steady metronome you imagine, but a flexible dimension that bends and stretches based on gravity and velocity. You'll find that the universe's structure, from the smallest subatomic particles to the largest galactic superclusters, emerges from the interplay between motion and the fundamental forces that govern it. Our journey begins in the realm of ultimate stillness, where temperature approaches absolute zero and quantum effects dominate. We will progress through the patient realm of geological time, where mountains rise and continents drift over millions of years. From there, we explore biological motion, where life has evolved solutions spanning 10 orders of magnitude in speed. Finally, we examine human technological achievements that have shattered natural barriers and propelled us toward the cosmic speed limit. Each stage of this progression reveals new principles and deeper truths. The transition from quantum stillness to geological motion illustrates how statistical mechanics governs large systems. The leap from geological time to biological speed demonstrates how evolution optimizes for different environmental niches. The progression from biological limits to technological achievements shows how human intelligence can transcend natural constraints through engineering and scientific understanding. Understanding these connections provides practical value beyond intellectual satisfaction. Modern medicine depends on manipulating molecular motions within cells. Climate science requires modeling the complex interactions between atmospheric, oceanic, and geological processes operating on vastly different timescales. space exploration demands precise calculations of orbital mechanics and relativistic effects. Even everyday activities like cooking rely on controlling molecular motions through temperature and chemical reactions. The mathematical relationships governing these phenomena reveal the universe's underlying mathematical structure. The kinetic theory of gases connects temperature to molecular motion through the relationship where temperature equals 2/3 times the average kinetic energy divided by Boltzmann's constant. Einstein's special relativity shows how time dilation factor equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. These equations are not mere abstractions, but practical tools that enable technologies from medical imaging to particle accelerators. But mathematics alone cannot capture the full wonder of these discoveries. The realization that quantum tunneling allows chemical reactions to occur at temperatures where classical physics predicts they should be impossible challenges our intuitive understanding of causation itself. The fact that gravitational time dilation means that clocks run slightly faster in your attic than in your basement forces us to reconsider the nature of time itself. The discovery that cosmic expansion can carry galaxies away from us faster than light speed without violating relativity reveals that space itself is a dynamic, evolving entity. These insights accumulate to paint a picture of reality far stranger and more magnificent than everyday experience suggests. We inhabit a universe where the familiar concepts of motion and rest, fast and slow, near and far, are revealed as limited approximations valid only within narrow ranges of scale and circumstance. The true nature of reality encompasses phenomena so extreme that they stretch language and imagination to their limits. Yet this strangeness comes with profound beauty. The same physical laws that govern the quantum vacuum also determine stellar evolution. The mathematical symmetries that appear in particle physics also manifest in the large-scale structure of the cosmos. The conservation principles that regulate energy and momentum apply equally to chemical reactions in living cells and to the formation of galaxies billions of light-years away. This universality suggests something remarkable about the nature of physical law itself. The universe appears to be constructed according to mathematical principles of extraordinary elegance and generality. The patterns we discover at one scale often repeat with variations at completely different scales. This self-similarity across scales hints at deep organizational principles that we are only beginning to understand. Our exploration will reveal these patterns and connections, building understanding systematically from the familiar to the extraordinary. By the end of this journey, you will possess a framework for understanding motion and speed that spans the entire known universe, from the quantum realm to cosmic horizons. You will understand why nothing can travel faster than light, why time is relative, why space can expand, and how these principles shape everything from the stability of atoms to the evolution of the cosmos itself. Most importantly, you will develop an intuitive feel for the scales and relationships that govern physical reality. This intuition will serve as a foundation for understanding new discoveries and technologies as they emerge. The principles you master here will remain valid regardless of what future research reveals about the nature of reality at its deepest levels. The universe's story is ultimately a story about motion, energy, and the transformations they enable. From the first moments after the Big Bang, when space itself expanded faster than light, to the present era, where complex chemical reactions sustain life on at least one planet, motion has been the driving force behind every significant development in cosmic history. Understanding motion in its full range means understanding the universe itself. Deep within the most sophisticated laboratories on Earth, scientists routinely achieve conditions more extreme than those found anywhere in the observable universe. They create temperatures so cold that the very concept of heat becomes meaningless, where atoms approach a state of perfect stillness that would make time itself seem frozen. This realm of ultimate cold represents not merely the absence of warmth, but the approach toward a fundamental limit of nature itself. To understand absolute zero, we must first understand what temperature actually measures. Temperature is not the presence or absence of some mysterious substance called heat, but rather a measure of the average kinetic energy of particles in a system. When a gas feels hot, its molecules are moving rapidly, colliding with each other and with container walls with tremendous energy. When the same gas cools, these molecular motions slow down. Temperature, measured in Kelvin, directly reflects this molecular activity through the relationship where the average kinetic energy equals 3/2 times Boltzmann's constant times temperature. As temperature drops toward absolute zero, defined as 0 Kelvin or negative 273.15 degrees Celsius, something extraordinary happens. The random thermal motions that normally dominate molecular behavior begin to disappear. Atoms and molecules slow their frantic dance, and quantum mechanical effects that are normally overwhelmed by thermal noise begin to emerge and dominate. At 1 Kelvin, above absolute zero, helium atoms move at speeds of roughly 150 meters per second. This might seem fast, but consider that at room temperature, the same atoms zip around at over 1,000 meters per second. At 1,000th of a Kelvin, these speeds drop to mere centimeters per second. As we approach closer and closer to absolute zero, the atomic motion becomes increasingly sluggish. But here we encounter one of quantum mechanics' most fundamental principles. The Heisenberg uncertainty principle prevents us from ever reaching true absolute zero. This principle states that the product of uncertainties in position and momentum must always exceed Planck's constant divided by 4pi. If atoms were to stop moving completely, we would know their momentum exactly, which would make their position completely uncertain. This quantum mechanical constraint means that even at absolute zero, atoms retain what physicists call zero-point motion, a minimum level of kinetic energy that can never be eliminated. Yet scientists have achieved temperatures within billionths of a Kelvin above absolute zero, creating conditions where quantum effects produce behaviors that seem to violate common sense. At these temperatures, entire groups of atoms can occupy identical quantum states, forming what physicists call Bose-Einstein condensates. In these exotic states of matter, thousands or millions of atoms behave as a single giant quantum object, exhibiting properties like superfluidity, where the substance can flow without any friction whatsoever. The pursuit of absolute zero has revealed profound truths about the quantum nature of reality. As classical thermal motion disappears, quantum tunneling effects become increasingly important. This phenomenon allows particles to pass through energy barriers that should be classically impenetrable, like a ball rolling up and over a hill without having enough energy to reach the top. At extremely low temperatures, chemical reactions that should be impossible according to classical physics can still occur through this quantum tunneling process. Scientists have observed chemical reactions between hydrogen ions that proceed at rates millions of times slower than room temperature reactions. In these ultra-cold experiments, hydrogen ions H+ and molecular hydrogen H2 approach each other with such little kinetic energy that they rarely collide with sufficient force to react. Classical physics would predict that the reaction rate should approach zero as temperature drops. Instead, quantum tunneling allows the reaction to continue, albeit at an extraordinarily slow pace, with successful reactions occurring perhaps once in every 100 billion collisions. This quantum tunneling effect demonstrates how the microscopic world operates according to rules that seem to contradict everyday experience. The probability of tunneling depends exponentially on the barrier height and width, following relationships derived from Schrödinger's equation. As temperature drops and classical kinetic energy becomes insufficient to surmount reaction barriers, tunneling probability begins to dominate the reaction kinetics. The mathematics describing these processes involves complex wave functions and probability amplitudes that have no direct analogue in classical physics. Understanding these ultra-cold phenomena has practical applications that extend far beyond academic curiosity. Quantum computers depend on maintaining quantum coherence at extremely low temperatures, where thermal noise cannot disrupt delicate quantum states. Superconductors, which can carry electrical current with zero resistance, only function below specific critical temperatures, where thermal motion cannot disrupt the Cooper pairs that enable loss-free current flow. The magnetic resonance imaging machines used in medical diagnosis rely on liquid helium cooling to maintain superconducting magnets that generate magnetic fields tens of thousands of times stronger than Earth's magnetic field. These magnets must be kept at temperatures below 4.2 Kelvin to maintain their superconducting properties. The precise control of atomic motion at these temperatures enables medical imaging with resolution sufficient to detect tumors just millimeters in size. The study of ultra-cold gases has also revealed unexpected connections between seemingly unrelated areas of physics. The mathematical equations describing ultra-cold atomic gases turn out to be identical to those describing high-temperature superconductors and even certain aspects of black hole physics. This universality of mathematical description suggests deep underlying connections between phenomena that operate at vastly different scales and energy ranges. Perhaps most remarkably, the approach toward absolute zero reveals the quantum mechanical nature of space and time themselves. At extremely low temperatures, the quantum vacuum becomes increasingly important. Even completely empty space contains quantum fluctuations, virtual particles that spontaneously appear and disappear on timescales so brief that they normally remain undetectable. These vacuum fluctuations contribute measurable effects, such as the Casimir force between closely spaced conducting plates, demonstrating that even absolute emptiness possesses a complex quantum structure. The precision required to approach absolute zero has driven technological innovations with applications throughout science and industry. Laser cooling techniques, which use precisely tuned laser light to slow atomic motion, have achieved temperatures in the nanokelvin range. These methods work by exploiting the Doppler effect, where atoms moving toward a laser beam see slightly blue-shifted light that becomes resonant with atomic transitions, causing the atoms to absorb photons and slow down through momentum conservation. Magnetic trapping techniques complement laser cooling by using carefully designed magnetic field configurations to confine ultra-cold atoms in space. These traps can hold millions of atoms at temperatures measured in nanokelvins, creating pristine environments for studying quantum phenomena without interference from thermal motion or environmental contamination. The mathematical description of these ultra-cold systems requires sophisticated quantum field theory techniques originally developed for particle physics and cosmology. The partition functions describing thermal equilibrium at these temperatures involve quantum statistical mechanics, where Fermi-Dirac or Bose-Einstein statistics replace classical Maxwell-Boltzmann distributions. The resulting mathematics reveals phase transitions and critical phenomena that mirror those found in condensed matter physics and even in the early universe. But perhaps the most profound insight from ultra-cold physics concerns the nature of time itself, near absolute zero. At these temperatures, characteristic timescales for atomic processes stretch from femtoseconds to seconds or even minutes. Chemical reaction rates that normally occur billions of times per second slow to rates measured in hertz or millihertz. This dramatic slowing reveals time not as an absolute universal constant, but as an emergent property intimately connected to the energy scales and dynamics of the systems we observe. The exploration of absolute zero thus opens a window into fundamental questions about the nature of physical reality. It reveals quantum mechanics not as an abstract mathematical formalism, but as the underlying operational manual that governs atomic and molecular behavior, when thermal noise no longer masks these effects. The techniques developed for achieving and maintaining ultra-cold conditions continue to drive advances in quantum technology, precision measurement, and our understanding of phase transitions and critical phenomena. As we move forward from this realm of ultimate stillness, we encounter the next level of cosmic patience, the geological processes that shape planets and reshape continents over millions of years. The transition from quantum stillness to geological motion represents a fundamental shift in scale, from individual atoms approaching perfect rest to massive tectonic forces that move mountains grain by grain across vast expanses of time. The earth beneath your feet appears solid and permanent, yet it participates in a slow-motion dance that reshapes continents, builds mountain ranges, and sculpts ocean basins over timescales that dwarf human civilization. This geological choreography operates at speeds so gradual that entire human lifetimes represent mere moments in its grand progression. Yet the forces involved exceed anything in human experience by orders of magnitude. Plate tectonics, the theory that revolutionized geology in the 20th century, reveals that Earth's seemingly solid surface consists of enormous slabs of rock floating on a partially molten interior. These tectonic plates move at speeds typically measured in centimeters per year, roughly equivalent to the rate at which your fingernails grow. The North American plate creeps westward at approximately 2.5 centimeters annually, while the Pacific plate slides northwestward at 8 to 10 centimeters per year. These measurements, obtained through decades of precise satellite positioning and ground-based surveying, document continental drift with accuracy that would have amazed Alfred Wegener, who first proposed the theory in 1912. The driving mechanism behind this continental ballet involves convection currents within Earth's mantle, a layer of hot plastic rock extending from 30 kilometers below the surface to the core mantle boundary 2,900 kilometers down. Temperature differences between the core mantle boundary, where temperatures exceed 4,000 degrees Celsius, and the relatively cool upper mantle create density variations that drive slow convection patterns. Hot material rises toward the surface, cools, spreads laterally, then eventually sinks back toward the core in a process that operates over millions of years. Understanding mantle convection requires grappling with fluid dynamics at conditions impossible to replicate in any laboratory. The mantle behaves as both solid and liquid, depending on the time scale considered. Over short periods measured in seconds or minutes, mantle rock responds to stress as a rigid solid. Over geological timescales measured in millions of years, the same rock flows like an extremely viscous liquid, with viscosity approximately 10 to the 21st power times greater than water. This dual solid-liquid behavior, described mathematically by viscoelastic theory, explains how solid rock can flow and deform while maintaining its crystalline structure. The mathematical description of mantle convection involves the Navier-Stokes equations modified for highly viscous flow, coupled with heat transfer equations and equations of state, describing how rock properties change with temperature and pressure. The Rayleigh number, which equals thermal expansion, coefficient times gravity times density times temperature difference times characteristic length cubed, divided by thermal diffusivity times viscosity, determines whether convection will occur. For Earth's mantle, Rayleigh numbers exceed the critical value by factors of millions, ensuring vigorous convection despite the enormous viscosity. Where tectonic plates separate, new oceanic crust forms through seafloor spreading. Mid-ocean ridges, underwater mountain ranges that encircle the globe like seams on a baseball, mark these spreading centers. Here, upwelling mantle material melts due to decompression, creating basaltic magma that solidifies into new oceanic crust. The mid-Atlantic ridge spreads at roughly 2 to 5 centimeters per year, literally creating new ocean floor and pushing Europe and North America farther apart. This process has operated continuously for over 200 million years, completely renewing the oceanic crust multiple times throughout Earth's history. The age distribution of oceanic crust provides compelling evidence for seafloor spreading rates and patterns. Magnetic stripes in oceanic basalt, created when iron-bearing minerals align with Earth's magnetic field during cooling, preserve a record of magnetic field reversals spanning millions of years. These magnetic anomalies, discovered through systematic ocean surveys in the 1950s and 60s, demonstrate that oceanic crust forms symmetrically at ridge axes and spreads outward at measurable rates. The mathematical analysis of these magnetic patterns requires understanding both paleomagnetism and statistical signal processing techniques to extract spreading rates from noisy geophysical data. Where oceanic plates encounter continental plates, subduction occurs, with oceanic crust diving beneath continental masses and descending into the mantle. The Nazca Plate, for example, subducts beneath the South American plate at approximately 6 centimeters per year, generating the volcanic Andes Mountains and creating the Peru-Chile Trench, the deepest point in the Pacific Ocean. Subduction zones represent some of Earth's most dynamic geological environments, producing earthquakes, volcanic eruptions, and mountain building through processes that operate across multiple timescales. The mechanics of subduction involve complex interactions between gravitational forces, buoyancy effects, and viscous resistance within the mantle. As oceanic plates age and cool, they become denser and more likely to sink into the mantle. The negative buoyancy of cold oceanic lithosphere provides the primary driving force for plate tectonics, creating what geophysicists call slab pull. Mathematical models of subduction require solving coupled systems of differential equations describing thermal evolution, mechanical deformation, and phase transitions in descending slabs. Continental collision zones, where two continental plates meet, create some of Earth's most spectacular topographic features. The ongoing collision between the Indian and Eurasian plates, which began approximately 50 million years ago, continues to build the Himalayan mountain range at rates of several millimeters per year. This collision has already elevated peaks above 8,000 meters and continues to drive uplift that more than compensates for erosional processes attempting to level the mountains. The complex three-dimensional geometry of this collision zone requires sophisticated finite element modeling to understand the distribution of stresses and deformation rates throughout the region. Transform faults where plates slide past each other horizontally provide another window into the mechanics of slow geological motion. The San Andreas fault system accommodates approximately 5 centimeters per year of relative motion between the Pacific and North American plates through a complex network of interconnected fault segments. The stick-slip behavior of transform faults, where motion occurs through periodic earthquakes separated by long periods of elastic strain accumulation, illustrates how geological processes can shift abruptly between different timescales. The mathematical description of fault mechanics involves concepts from fracture mechanics and friction theory. The relationship between shear stress and normal stress on fault surfaces follows empirical laws like Byerlee's law, which states that shear stress equals friction coefficient times normal stress plus cohesive strength. Critical stress thresholds determine when accumulated elastic strain will release suddenly during earthquakes, connecting the gradual loading of tectonic stresses to the rapid slip that produces seismic waves. Glacial processes operate on similar timescales to tectonic motion, but through completely different physical mechanisms. Mountain glaciers, fed by accumulated snowfall over decades or centuries, flow downhill under gravitational stress at rates typically measured in meters per year. The Glacier Bay system in Alaska has retreated over 100 kilometers since 1750, documenting glacial response to climate variations over centuries. These retreat rates, measured through historical records, satellite imagery and geological evidence, provide crucial data for understanding how ice masses respond to changing environmental conditions. Glacier flow involves ice deformation through dislocation creep, where crystal defects migrate through the ice lattice under applied stress. Glenn's law describes the relationship between strain rate and stress for ice deformation, with strain rate proportional to stress raised to the power n, where n typically equals 3. This non-linear relationship means that small increases in gravitational stress can produce large increases in flow rate, explaining why glacier flow rates depend sensitively on ice thickness and surface slope. The mathematical modeling of glacier dynamics requires solving the Stokes equations for highly viscous flow, coupled with mass conservation equations and thermal evolution equations. Ice viscosity depends exponentially on temperature through an Arrhenius relationship, making thermal modeling crucial for accurate flow predictions. Modern glacier models employ sophisticated finite element techniques to capture the complex three-dimensional geometry of ice flow over realistic topography. Ice sheet dynamics operate on even grander scales, with the Greenland and Antarctic ice sheets containing sufficient frozen water to raise global sea level by 7 and 58 meters respectively, if completely melted. These ice sheets flow from central accumulation zones toward marine margins where icebergs carve into the ocean. Flow velocities range from centimeters per year in central regions to several kilometers per year in fast-flowing outlet glaciers and ice streams. The West Antarctic ice sheet presents particular challenges for understanding ice sheet stability because much of its base lies below sea level, making it potentially susceptible to marine ice sheet instability. This process, where retreat of grounding lines onto retrograde slopes can become self-reinforcing, could lead to rapid collapse of large portions of the ice sheet over centuries rather than millennia. Mathematical models of marine ice sheet dynamics require careful treatment of grounding line migration and the coupling between ice flow, ocean temperatures, and sea level changes. Geological processes also operate through chemical weathering, where rock minerals react with atmospheric gases and surface water to produce soluble products that rivers carry to the oceans. The global carbon cycle depends critically on chemical weathering of silicate minerals, which consumes atmospheric carbon dioxide and produces bicarbonate ions that eventually precipitate as marine carbonates. This process operates as a negative feedback mechanism that helps stabilize Earth's climate over geological timescales, but the characteristic response time exceeds 100,000 years. The mathematical description of chemical weathering involves reaction kinetics equations coupled with transport processes in soil and groundwater systems. Our weathering rates depend on temperature, precipitation, and rock composition through complex relationships that researchers continue to investigate through field studies and laboratory experiments. Understanding these relationships becomes increasingly important as human activities alter atmospheric composition and climate patterns that have remained relatively stable throughout human history. Erosional processes complement weathering by physically removing material from elevated regions and transporting it toward lower elevations and ultimately to the oceans. River systems driven by the hydrological cycle carry approximately 25 billion tons of sediment to the oceans annually. This erosional flux balances mountain-building processes over geological timescales, maintaining dynamic equilibrium between tectonic uplift and surface denudation. The mathematical modeling of erosional processes involves understanding how flowing water entrains, transports, and deposits sediment particles. The Hjulström-Sundborg diagram relates flow velocity to grain size for sediment transport, showing that fine particles require higher velocities for entrainment than for transport due to cohesive forces between clay minerals. These relationships, derived from extensive laboratory and field studies, form the basis for quantitative models of landscape evolution over geological timescales. The integration of all these geological processes creates Earth's complex surface topography and internal structure. Mountain ranges rise through tectonic forces, while erosional processes sculpture detailed landforms and transport material towards sedimentary basins. The competition between uplift and erosion determines the elevation and relief of mountain ranges, with characteristic timescales for landscape evolution ranging from thousands to millions of years, depending on tectonic and climatic conditions. Understanding geological processes requires grappling with the concept of deep time, where events that seem impossibly slow from human perspectives become rapid when viewed against the 4.5 billion-year history of Earth. The Grand Canyon, carved by the Colorado River over the past 6 million years, represents rapid erosion compared to the 2-billion-year-old rocks exposed in its depths. This perspective shift from human to geological timescales provides essential context for understanding how the apparently permanent features of Earth's surface actually represent momentary snapshots of ongoing dynamic processes. The study of geological motion has revealed fundamental insights about planetary evolution and the conditions necessary for maintaining habitable environments over billions of years. Plate tectonics plays crucial roles in climate regulation through the carbon cycle, in generating Earth's magnetic field through core dynamics, and in concentrating mineral resources through various geological processes. Without the slow dance of tectonic plates, Earth might resemble Venus or Mars, with stagnant surfaces and atmospheres that have evolved away from conditions suitable for life as we know it. As we transition from geological to biological timescales, we encounter life forms that have evolved solutions to the challenge of motion across an enormous range of speeds and environmental conditions. The patient processes that build mountains and move continents provide the stage upon which biological evolution creates its own spectacular range of motion. From creatures that barely move to others that achieve speeds approaching the theoretical limits for biological systems. Life has conquered motion across a spectacular range that spans nearly 8 orders of magnitude, from bacteria that drift with imperceptible slowness to predators that strike faster than human reflexes can follow. This biological mastery of speed reflects 4 billion years of evolutionary optimization, where natural selection has fine-tuned locomotion strategies for every conceivable ecological niche, environmental challenge and survival requirement. Understanding biological motion requires appreciating the fundamental physics that constrains living systems. Unlike engineered machines, which can separate power generation from mechanical motion, biological systems must integrate energy production, structural support, sensory processing, and locomotion within the same cellular and tissue frameworks. Every movement demands coordination between metabolic processes that convert chemical energy into mechanical work, sensory systems that provide feedback about environmental conditions, and control mechanisms that coordinate complex patterns of muscle activation. The smallest motile organisms face physics fundamentally different from larger creatures. Bacteria swimming through water experience viscous forces that completely dominate inertial effects, creating what fluid dynamicists call low Reynolds number flow. The Reynolds number, calculated as density times velocity times characteristic length divided by viscosity, determines the relative importance of inertial versus viscous forces in fluid motion. For bacteria swimming at typical speeds of 10 to 50 micrometers per second, Reynolds numbers fall below 1, meaning viscous forces exceed inertial forces by orders of magnitude. In this low Reynolds number regime, conventional swimming strategies become impossible. If a bacterium simply wiggled back and forth like a fish, viscous forces would exactly reverse any forward motion during the return stroke, resulting in zero net displacement. Instead, bacteria have evolved rotating helical flagella that function like microscopic corkscrews, converting rotary motion into forward thrust through asymmetric interactions with the surrounding fluid. This propulsion mechanism, powered by rotary motors embedded in the bacterial cell membrane, achieves efficiencies that rival or exceed human-designed propulsion systems. The bacterial flagella motor represents one of biology's most sophisticated molecular machines. This protein complex consists of dozens of different components assembled into a structure that spans the cell membrane and generates torque through controlled ion gradients. Protons, or sodium ions flowing down electrochemical gradients, provide the energy source, with each ion passage linked mechanically to small rotational increments of the central rotor. The resulting motor produces torques exceeding 1,000 piconewton nanometers while rotating at frequencies up to 1,000 Hz, generating power densities comparable to automotive engines. At the opposite extreme of biological motion, large vertebrates have evolved locomotion strategies that exploit inertial effects to achieve remarkable efficiency and speed. The physics of terrestrial locomotion involves complex interactions between gravitational potential energy, kinetic energy, and elastic energy storage in tendons and other connective tissues. Running animals convert these energy forms cyclically, storing elastic energy during the loading phase of each stride and releasing it to supplement muscular work during the propulsive phase. The mathematical description of animal locomotion involves biomechanical analysis of the forces acting on body segments, coupled with metabolic analysis of energy consumption rates. The cost of transport, defined as metabolic power consumption divided by body weight times velocity, provides a standardized measure for comparing locomotion efficiency across species. Remarkably, this cost of transport follows predictable scaling relationships with body size, with larger animals generally achieving more efficient transport per unit body weight than smaller animals. Terrestrial speed champions have evolved structural and physiological adaptations that push the limits of biological performance. The cheetah achieves maximum speeds approaching 110 kilometers per hour through a combination of anatomical features optimized for acceleration and high-speed running. Extended spine flexibility allows stride lengths exceeding 7 meters, while enlarged heart and lung capacity provide the oxygen delivery rates necessary to sustain the intense metabolic demands of sprint hunting. The biomechanics of cheetah locomotion involves precise coordination between spinal flexion and extension, limb movements, and respiratory cycles. High-speed cinematography reveals that cheetahs spend more than half of each stride completely airborne, with all 4 legs off the ground simultaneously. This ballistic phase allows the spine to extend fully, maximizing stride length and enabling the rapid repositioning of limbs for the next ground contact. The mathematical analysis of this gait pattern requires understanding the projectile motion of the body's center of mass, coupled with the complex dynamics of leg positioning and ground contact forces. Aquatic environments present different opportunities and constraints for high-speed locomotion. Water density exceeds air density by approximately 800 times, providing greater reaction mass for propulsive forces, but also creating higher drag resistance. The fastest marine animals have evolved body shapes and swimming techniques that minimize drag while maximizing propulsive efficiency through sophisticated undulatory motions. Sailfish achieve swimming speeds exceeding 100 kilometers per hour through undulatory propulsion that creates traveling waves along their body length. The mathematics of undulatory swimming involves wave mechanics, where the fish body generates backward traveling waves that push against the water to create forward thrust. The optimal relationship between wave amplitude, wavelength, and frequency depends on body geometry and swimming speed, leading to complex optimization problems that fish solve through evolutionary trial and error over millions of generations. The hydrodynamic efficiency of fish swimming approaches theoretical limits predicted by fluid dynamic analysis. The wake structure behind fast-swimming fish shows remarkably little energy waste, with most of the kinetic energy imparted to the water directed backward to create forward thrust. This efficiency results from billions of years of evolutionary optimization, where even small improvements in swimming performance provided survival advantages that accumulated through natural selection. Aerial locomotion presents the ultimate challenge for biological motion systems. Flight requires generating lift forces that exceed body weight while maintaining sufficient thrust to overcome drag and enable forward motion. The power requirements for flapping flight scale unfavorably with body size, limiting the maximum size of flying animals and requiring sophisticated control mechanisms to maintain stable flight. Birds have evolved multiple solutions to the aerodynamic challenges of flapping flight. The peregrine falcon achieves diving speeds exceeding 320 kilometers per hour by transforming potential energy into kinetic energy while using precise wing and tail adjustments to control descent trajectory. During these spectacular hunting dives, peregrines experience accelerations that would incapacitate human pilots, requiring specialized cardiovascular and respiratory adaptations to maintain consciousness and motor control. The mathematics of peregrine diving involves ballistics modified by aerodynamic effects. Drag forces increase with the square of velocity, eventually balancing gravitational forces to establish a terminal velocity that depends on wing configuration and body orientation. Peregrines can modify their terminal velocity by adjusting wing position and body attitude, allowing precise control over diving speed and trajectory, while maintaining the ability to pull out of dives without structural damage. Insect flight operates through completely different mechanisms than bird flight, exploiting unsteady aerodynamic effects that remain incompletely understood despite decades of research. Many insects generate lift through figure-8 wing motions that create complex vortex structures, enabling flight performance that exceeds predictions from conventional steady-state aerodynamic analysis. Hummingbirds, though not insects, employ similar unsteady aerodynamic mechanisms that allow them to hover, fly backward, and maneuver with precision impossible for conventional aircraft. The control systems underlying animal locomotion represent sophisticated solutions to complex engineering problems. Nervous systems must integrate sensory information about environmental conditions, body position, and movement goals to generate appropriate motor commands in real time. This sensor-motor integration involves distributed processing across multiple brain regions, spinal circuits, and peripheral sensors, creating control architectures that adapt continuously to changing conditions. Recent advances in biomechanics have revealed the crucial role of passive mechanical properties in animal locomotion. Tendons, ligaments, and other elastic structures store and release energy during locomotion cycles, reducing the metabolic demands on muscle systems while providing mechanical stability and responsiveness. The spring-like properties of these tissues follow mathematical relationships derived from materials science, with elastic moduli and energy storage capacities that have been optimized through evolutionary processes. Understanding the scaling relationships that govern animal locomotion provides insights into the physical constraints that shape evolutionary trajectories. Metabolic power scales with body mass raised to approximately 3/4 power, while the mechanical power required for locomotion scales differently depending on the mode of transport. These scaling relationships explain why large animals cannot move as quickly relative to their body size as small animals, and why there are fundamental limits to the size and speed combinations achievable through biological systems. The study of animal locomotion has inspired technological innovations ranging from robotic systems to transportation vehicles. Bio-inspired robotics attempts to replicate the efficiency and adaptability of biological motion systems, while transportation engineers study animal locomotion for insights into drag reduction, energy efficiency, and control system design. The convergent evolution of high-speed locomotion across different animal lineages suggests that the physical principles governing efficient motion are universal, providing design guidelines that transcend the boundary between biological and artificial systems. The diversity of biological motion strategies reflects the enormous range of environmental conditions and ecological niches that life has colonized. From the microscopic world, where viscous forces dominate, to terrestrial environments where gravity and inertia shape locomotion strategies, to aquatic and aerial environments where fluid dynamics determines performance limits, life has found solutions that often approach theoretical optimality predicted by physical analysis. This biological mastery of motion across such an enormous range of scales and conditions sets the stage for understanding how human technology has begun to transcend the limitations that constrain biological systems. While evolution operates through gradual modifications over millions of years, human engineering can implement radical design changes within single generations, enabling technological achievements that surpass biological capabilities across multiple performance dimensions. Human ingenuity has shattered every speed barrier that evolution spent billions of years establishing. In less than a century, we progressed from the first powered flight to spacecraft traveling at velocities that would circumnavigate Earth in 90 minutes. This technological revolution in motion represents not merely incremental improvements over biological systems, but fundamental paradigm shifts that exploit physical principles unavailable to living organisms. The conquest of supersonic flight exemplifies humanity's systematic approach to overcoming seemingly insurmountable physical barriers. When Chuck Yeager piloted the Bell X-1 through the sound barrier on October 14, 1947, he confronted aerodynamic phenomena that had puzzled engineers for decades. The speed of sound in air, approximately 343 meters per second at sea level, represents a fundamental transition point where the behavior of flowing air changes dramatically. Understanding supersonic flight requires grappling with compressible flow dynamics, where air density variations become significant, and shock waves form whenever objects exceed local sound speed. The mathematics governing these phenomena involves the compressible Navier-Stokes equations, coupled with thermodynamic relationships, describing how air pressure, temperature, and density change through shock waves and expansion regions. These equations predict that drag forces increase dramatically as aircraft approach Mach 1, creating what engineers call the sound barrier. The physical mechanisms underlying the sound barrier involve the formation of shock waves that propagate at exactly the local sound speed. When an aircraft travels at subsonic speeds, pressure disturbances from its motion can propagate ahead of the vehicle, allowing air to flow smoothly around the aircraft surfaces. As the aircraft speed approaches the sound speed, these pressure signals can no longer outrun the vehicle, causing them to accumulate into shock waves that create sudden pressure jumps and dramatic increases in aerodynamic resistance. Overcoming the sound barrier required revolutionary changes in aircraft design philosophy. Subsonic aircraft achieve efficiency through thick, cambered wing sections that generate lift through smooth pressure distributions over wing surfaces. Supersonic aircraft demand thin, sharp-edged wings that minimize shockwave formation and reduce wave drag. The mathematical optimization of supersonic wing geometry involves area ruling, where aircraft cross-sectional area must vary smoothly along the fuselage length to minimize shockwave interference effects. The Bell X-1's rocket propulsion system provided crucial advantages for supersonic flight research. Rocket engines, unlike air-breathing engines, maintain constant thrust regardless of flight speed and altitude, enabling acceleration through the transonic speed range where conventional propulsion systems lose efficiency. The rocket principle operates through Newton's third law, where high-velocity exhaust gases create reaction forces that propel the vehicle forward. The specific impulse of rocket propulsion, measured in seconds, equals exhaust velocity divided by gravitational acceleration, providing a standardized measure of propulsion efficiency. Modern supersonic aircraft routinely exceed Mach 2, with specialized vehicles like the Lockheed SR-71 Blackbird achieving sustained flight at Mach 3.3. At these speeds, aerodynamic heating becomes a dominant design constraint, with surface temperatures exceeding 400 degrees Celsius due to viscous dissipation in the boundary layer. The mathematical description of aerodynamic heating involves solving the coupled momentum and energy equations for compressible boundary layer flow, where kinetic energy converts to thermal energy through viscous friction effects. The material science challenges of high-speed flight have driven innovations in metallurgy, ceramics, and composite materials. Titanium alloys, chosen for their strength-to-weight ratio and temperature resistance, enable aircraft structures that maintain integrity under extreme thermal and mechanical loads. The thermal expansion coefficients of these materials must be carefully matched to prevent thermal stress concentrations that could cause structural failure during high-speed flight. Terrestrial speed records have pushed wheeled vehicles beyond the sound barrier, with the thrust supersonic car achieving 1,228 kilometers per hour in 1997. This achievement required solving unique engineering challenges related to wheel dynamics at supersonic speeds, where conventional tire technology becomes impossible due to centrifugal forces and aerodynamic heating. The thrust SSC employed solid aluminum wheels designed to withstand rotational speeds exceeding 10,000 revolutions per minute while maintaining structural integrity under extreme loading conditions. The aerodynamics of supersonic ground vehicles differ fundamentally from aircraft due to ground effect interactions and the requirement to maintain wheel contact with the surface. Shockwave reflections from the ground create complex pressure field patterns that affect vehicle stability and control. The mathematical modeling of these phenomena requires computational fluid dynamics techniques capable of resolving multiple shockwave interactions and boundary layer effects simultaneously. Rocket propulsion has enabled humanity's most dramatic speed achievements, culminating in spacecraft velocities that exceed anything possible within Earth's atmosphere. The physics of rocket propulsion follows directly from conservation of momentum, where the momentum change of exhaust gases equals the momentum change of the spacecraft. The rocket equation derived by Konstantin Tsiolkovsky in 1897 relates the velocity change achievable by a rocket to the exhaust velocity and the ratio of initial to final mass. Delta V equals exhaust velocity times natural logarithm of initial mass divided by final mass. This exponential relationship explains why achieving high spacecraft velocities requires enormous fuel mass ratios. To reach Earth orbit, which requires approximately 9 kilometers per second velocity change, typical chemical rockets must carry propellant masses exceeding 90% of their initial launch weight. The tyranny of the rocket equation has driven continuous innovation in propulsion technology and mission design strategies to minimize the performance penalties associated with Earth's deep gravitational well. Escape velocity from Earth's surface equals the square root of 2 times gravitational parameter divided by planetary radius, approximately 11.2 kilometers per second. This represents the minimum velocity required for an object to escape Earth's gravitational influence completely, assuming no atmospheric drag or other energy losses. Achieving escape velocity requires spacecraft to gain kinetic energy equal to their gravitational binding energy, demonstrating the direct connection between energy and motion that underlies all transportation systems. NASA's Parker Solar Probe represents the pinnacle of spacecraft velocity achievement, reaching perihelion speeds exceeding 690,000 kilometers per hour during its closest solar approaches. This extraordinary velocity results from gravitational acceleration as the spacecraft falls toward the Sun, converting gravitational potential energy into kinetic energy according to conservation of energy principles. The probe's elliptical orbit enables it to gain speed during each solar approach, while using Venus gravity assists to progressively reduce its perihelion distance and increase maximum velocity. The engineering challenges of extreme spacecraft velocity involve thermal protection, navigation accuracy, and communication systems that must function under conditions impossible to replicate in ground-based testing. At Parker Solar Probe's maximum speed, the spacecraft travels nearly 200 kilometers per second, requiring autonomous navigation systems that can adjust trajectory without ground-based intervention due to communication delays exceeding 8 minutes each way. Hypersonic flight, defined as speeds exceeding Mach 5, represents the current frontier of atmospheric flight technology. At these velocities, air molecules dissociate due to extreme temperatures generated by compression heating, creating plasma flows that interact with electromagnetic fields. The physics of hypersonic flight involves real gas effects, where air no longer behaves as an ideal gas with constant specific heats, requiring sophisticated thermochemical models to predict vehicle performance and heating rates. The X-15 rocket plane, operational from 1959 to 1968, achieved speeds exceeding Mach 6.7 and altitudes above 100 kilometers, technically reaching the edge of space. These flights provided crucial data about hypersonic aerodynamics, thermal protection systems, and pilot physiological responses to extreme flight conditions. The X-15's rocket engine generated over 250,000 newtons of thrust, enabling acceleration rates that subjected pilots to forces exceeding 6 times Earth's gravity. Modern hypersonic research focuses on air-breathing propulsion systems that could enable single-stage-to-orbit vehicles and ultra-high-speed atmospheric transport. Scramjet engines, which operate by compressing incoming air through vehicle geometry rather than mechanical compressors, offer theoretical advantages for hypersonic flight, but require complex inlet designs that must slow supersonic airflow to subsonic speeds while minimizing pressure losses and thermal loads. The mathematical modeling of scramjet performance involves solving the Euler equations for inviscid compressible flow, coupled with combustion chemistry equations describing fuel-air mixing and reaction kinetics. These calculations require sophisticated computational fluid dynamics codes running on supercomputers to capture the complex three-dimensional flow patterns and shock-wave interactions that determine engine performance. Ion propulsion systems represent a completely different approach to achieving high velocities in space, trading thrust magnitude for extremely high exhaust velocities. Ion thrusters accelerate charged particles through electric fields, achieving exhaust velocities exceeding 50 kilometers per second compared to approximately 4 kilometers per second for chemical rockets. While ion thrusters generate thrust measured in millinewtons rather than the hundreds of thousands of newtons produced by chemical rockets. Their superior fuel efficiency enables velocity changes that would be impossible with conventional propulsion. The physics of ion propulsion involves plasma dynamics and electromagnetic field interactions that follow Maxwell's equations and the Lorentz force law. Ions accelerated through electric potential differences gain kinetic energy equal to charge times potential difference, enabling precise control over exhaust velocity through electrical power regulation. The specific impulse of ion thrusters often exceeds 3,000 seconds, compared to approximately 450 seconds for the most efficient chemical rockets. Future propulsion concepts under investigation include fusion rockets, antimatter propulsion, and solar sails that could enable interstellar missions within human lifetimes. Fusion propulsion could theoretically achieve exhaust velocities exceeding 10% of light speed, reducing transit times to nearby stars from tens of thousands of years to centuries or decades. These advanced concepts require solving fundamental physics and engineering challenges that remain beyond current technological capabilities, but offer the potential for revolutionary advances in space transportation. Solar sails exploit radiation pressure from sunlight to generate thrust without requiring any propellant mass. The momentum carried by photons creates small but continuous forces on large reflective surfaces, enabling spacecraft to gradually accelerate to high velocities over extended periods. The mathematical description of solar sail dynamics involves understanding electromagnetic momentum transfer and orbital mechanics in the complex gravitational environment of the solar system. The development of supersonic and hypersonic flight has revealed fundamental relationships between energy, entropy, and information that apply broadly across engineering disciplines. High-speed flight generates entropy through viscous dissipation and shockwave formation, requiring careful energy management to achieve desired performance levels. These thermodynamic considerations connect aerospace engineering to broader principles that govern all energy conversion processes. Understanding machine-based speed achievements requires appreciating the role of feedback control systems that enable stable operation under extreme conditions. Aircraft flying at supersonic speeds must continuously adjust control surfaces to maintain stability in the face of rapidly changing aerodynamic loads and moments. These control systems implement sophisticated algorithms derived from control theory, using sensor feedback to generate corrective actions faster than human reflexes could respond. The transition from biological to mechanical speed capabilities represents more than quantitative improvements. It demonstrates qualitatively different approaches to the fundamental challenge of controlled motion through three-dimensional space. While biological systems achieve remarkable efficiency and adaptability within evolutionary constraints, engineered systems can exploit energy sources, materials, and control strategies that transcend biological limitations. This technological mastery of extreme velocities within Earth's environment sets the foundation for understanding cosmic motion, where natural processes routinely achieve speeds that dwarf human technological achievements. The same physical principles that enable supersonic flight and spacecraft propulsion also govern the motion of planets, stars, and galaxies across the universe, revealing the universal nature of the laws that connect human engineering achievements to cosmic phenomena. While humanity celebrates achieving speeds of hundreds of thousands of kilometers per hour with our most advanced spacecraft, we inhabit a cosmic environment where such velocities represent barely perceptible motion against the backdrop of natural celestial mechanics. Every second of your existence unfolds within multiple reference frames, moving at speeds that would liquefy any terrestrial vehicle. Yet these motions remain completely imperceptible to human senses due to the principle of inertial reference frames that Einstein would later formalize in his theories of relativity. Earth itself functions as a massive spacecraft racing through space at velocities that dwarf every human speed achievement. Our planet's orbital motion around the Sun occurs at approximately 107,000 kilometers per hour, a speed that would transport you from New York to Los Angeles in roughly 4 minutes. This orbital velocity results from the precise balance between Earth's inertial tendency to travel in a straight line and the Sun's gravitational attraction that continuously deflects our planet's trajectory into its elliptical orbital path. The mathematical description of planetary orbital motion follows Kepler's laws, derived empirically in the early 17th century, and later explained theoretically through Newton's law of universal gravitation. Kepler's second law states that a line connecting any planet to the Sun sweeps out equal areas in equal time intervals, a consequence of angular momentum conservation in the gravitational field. This relationship means that Earth moves fastest when closest to the Sun in early January and slowest when farthest away in early July, with velocity variations of approximately 3% throughout the orbital cycle. The gravitational parameter Gm for the Sun, where G represents the universal gravitational constant and m the solar mass, equals approximately 1.33 times 10 to the 20th power cubic meters per second squared. This fundamental quantity determines orbital velocities for all solar system objects through the relationship where velocity equals the square root of gravitational parameter divided by orbital radius for circular orbits, or more complex expressions for elliptical trajectories that account for varying distances throughout the orbital cycle. But Earth's orbital motion represents only one component of our cosmic velocity. The entire solar system orbits around the center of the Milky Way galaxy at speeds approaching 800,000 kilometers per hour. This galactic orbital motion occurs because our solar system lies approximately 26,000 light-years from the galactic center, embedded within one of the galaxy's spiral arms, where gravitational forces from the central supermassive black hole and the distributed mass of billions of stars combine to maintain our circular orbital trajectory. The physics governing galactic rotation presents challenges that have revolutionized our understanding of cosmic structure and composition. According to Newtonian mechanics, orbital velocities should decrease with distance from the galactic center, following the same mathematical relationships that govern planetary motion around the Sun. Instead, astronomical observations reveal that stellar orbital velocities remain approximately constant with galactic radius, a phenomenon that requires either modifications to gravitational theory or the presence of enormous amounts of invisible matter called dark matter. Galaxy rotation curves, which plot orbital velocity versus distance from the galactic center, provide compelling evidence for dark matter's existence. The observed flat rotation curves require approximately 5 times more mass than can be accounted for by visible stars, gas and dust. This dark matter component apparently forms an extended halo surrounding the visible galaxy, with a mass distribution that produces the gravitational forces necessary to maintain the observed orbital velocities at large galactic radii. The mathematical modeling of galaxy dynamics involves solving Poisson's equation for the gravitational potential produced by both visible and dark matter components, coupled with the equations of motion for stellar orbits within this combined gravitational field. These calculations require sophisticated numerical techniques because the mass distributions lack the spherical symmetry that would enable analytical solutions, necessitating computational approaches that can handle the complex three-dimensional geometry of real galaxies. Our solar system's galactic orbit also exhibits vertical oscillations that carry us above and below the galactic plane with periods of approximately 60 million years. These oscillations result from the gravitational restoring force exerted by matter distributed within the galactic disk, creating harmonic motion similar to a mass attached to a spring. Some researchers have proposed connections between these galactic oscillations and periodic mass extinction events in Earth's fossil record, though such correlations remain controversial and require additional investigation. The local group, which contains the Milky Way, Andromeda Galaxy, and dozens of smaller galaxies, moves through space at approximately 600 kilometers per second relative to the cosmic microwave background radiation. This motion reflects the gravitational influences of massive galaxy clusters and superclusters that create large-scale velocity fields throughout the observable universe. The cosmic microwave background provides a natural reference frame for measuring these large-scale motions because it represents the thermal radiation from the early universe, effectively defining a rest frame relative to the expanding cosmic background. Comets provide spectacular examples of high-speed motion within the solar system, with some long-period comets achieving velocities exceeding 70 kilometers per second when passing close to the Sun. These icy remnants from the outer solar system follow highly elliptical orbits that bring them from distances of thousands of astronomical units to perihelion passages within a few astronomical units of the Sun. The extreme orbital eccentricities of long-period comets result from their formation in the Oort cloud, a spherical distribution of icy objects surrounding the solar system at distances where solar gravitational forces barely exceed the tidal effects of nearby stars. Comet Hale-Bopp, visible to the naked eye during 1996 and 1997, followed an orbital path that carried it from beyond the orbit of Jupiter to a perihelion distance of approximately 9/10 of an astronomical unit from the Sun. At perihelion, this comet achieved velocities approaching 44 kilometers per second, demonstrating how gravitational acceleration can propel natural objects to speeds that exceed most human spacecraft achievements. The orbital period of Hale-Bopp spans approximately 2,400 years, illustrating the vast timescales associated with highly eccentric solar system orbits. The mathematical description of cometary motion requires solving the gravitational two-body problem, where comet trajectories follow conic sections determined by their total orbital energy. Comets with negative total energy follow elliptical orbits and remain gravitationally bound to the solar system, while those with positive total energy follow hyperbolic trajectories and escape to interstellar space after a single close passage. The boundary case of zero total energy corresponds to parabolic orbits that represent the minimum velocity required for escape from solar gravitational influence. Interplanetary spacecraft must navigate this complex gravitational environment to reach their destinations, exploiting the orbital motions of planets to gain additional velocity through gravitational slingshot maneuvers. The Voyager spacecraft, launched in 1977, used a rare planetary alignment to visit all 4 outer planets through a series of carefully planned gravitational assists. Each planetary encounter provided velocity increases that would have been impossible to achieve through rocket propulsion alone, enabling these spacecraft to reach the edge of the solar system within human lifetimes. The physics of gravitational slingshot maneuvers involves conservation of energy and momentum in the reference frame of the assisting planet. From the planet's perspective, the spacecraft approaches with some velocity, swings around the planet following a hyperbolic trajectory, and departs with the same speed but different direction. However, in the solar reference frame, the planetary motion adds vectorially to the spacecraft velocity, potentially providing substantial speed increases that depend on the spacecraft trajectory, geometry, and the planet's orbital velocity. Voyager 1 achieved its current velocity of approximately 17 kilometers per second through gravitational assists from Jupiter and Saturn, enabling it to become the first human-made object to enter interstellar space in 2012. The spacecraft's trajectory carried it beyond the heliopause, the boundary where solar wind pressure balances interstellar medium pressure, into a region where galactic cosmic rays dominate the local particle environment and solar magnetic field influences become negligible. The escape velocity from the solar system, calculated at Earth's orbital distance, equals approximately 42 kilometers per second. This represents the minimum velocity required for an object to overcome solar gravitational attraction completely and escape to interstellar space. Most spacecraft launched from Earth lack sufficient velocity to achieve solar escape, instead following heliocentric orbits that keep them gravitationally bound within the solar system unless they receive gravitational assists from planetary encounters. Asteroid impacts provide dramatic examples of high-velocity cosmic collisions that have shaped planetary evolution throughout solar system history. The Chicxulub impact event, which contributed to the extinction of non-avian dinosaurs 66 million years ago, involved an asteroid approximately 10 kilometers in diameter, traveling at estimated velocities between 20 and 40 kilometers per second. The kinetic energy of this impact, calculated as 1/2 times mass times velocity squared, exceeded the explosive yield of all nuclear weapons ever built by factors of millions. The mathematical modeling of hypervelocity impacts requires understanding shock wave physics and the equations of state for materials under extreme pressures and temperatures. Impact velocities exceeding a few kilometers per second generate shock pressures that exceed the strength of any known material, causing both projectile and target to behave as fluids during the collision process. The crater scaling relationships that connect impact to size, velocity and angle to final crater dimensions involve complex empirical functions derived from laboratory experiments and numerical simulations. Meteorite studies provide direct evidence for the high velocities achieved by small solar system objects. Most meteoroids enter Earth's atmosphere at velocities between 11 and 72 kilometers per second, with the velocity range determined by the orbital characteristics of their parent bodies and Earth's own orbital motion. Fast meteoroids often originate from long-period comets with highly eccentric orbits, while slower ones typically derive from asteroids with more circular orbits similar to Earth's. The atmospheric entry of high-velocity meteoroids creates spectacular meteor displays through a process called ablation, where kinetic energy converts to thermal energy through atmospheric friction. The mathematical description of meteor ablation involves solving coupled equations for atmospheric drag, heat transfer, and mass loss, with solutions that depend on meteoroid size, composition, entry angle, and atmospheric density profiles. Most meteoroids completely vaporize before reaching Earth's surface, but larger objects can survive atmospheric passage to become meteorites that provide samples of extraterrestrial materials for laboratory study. Jupiter's gravitational influence dominates the dynamics of small solar system objects, acting as both protector and threat to inner solar system planets. The planet's massive gravitational field can capture or deflect incoming comets and asteroids, reducing the impact frequency on terrestrial planets. However, Jupiter's influence can also perturb objects from the asteroid belt or Kuiper belt onto Earth-crossing orbits, creating potential impact hazards that space agencies now monitor through systematic sky surveys. The mathematical analysis of planetary protection by Jupiter requires understanding the restricted three-body problem, where the motion of small objects depends on gravitational forces from both the Sun and Jupiter. The complex dynamics of this system create chaotic regions where small changes in initial conditions lead to dramatically different long-term orbital evolution, making precise long-term predictions impossible for many solar system objects, despite the deterministic nature of gravitational interactions. Binary star systems demonstrate even more extreme examples of cosmic velocities, where stars orbit around their common center of mass at speeds that can exceed hundreds of kilometers per second. Close binary systems with orbital periods measured in hours or days require orbital velocities comparable to those of spacecraft near light speed, creating extreme gravitational environments where relativistic effects become important for accurate orbital calculations. The physics of binary star evolution involves mass transfer processes where material flows from one star to its companion through gravitational interactions and stellar winds. When a white dwarf star accretes material from a companion, the accumulated hydrogen can undergo explosive nuclear fusion in thermonuclear nova explosions that eject material at velocities exceeding 10,000 kilometers per second. These explosions demonstrate how gravitational potential energy and nuclear binding energy can accelerate matter to extreme velocities through natural astrophysical processes. Contact binary systems represent the extreme limit of binary star evolution, where two stars share a common outer atmosphere while orbiting around each other in periods of hours. The orbital velocities in such systems approach significant fractions of the speed of light, creating relativistic effects that influence both orbital dynamics and stellar structure. The mathematical modeling of contact binaries requires general relativistic calculations that account for gravitational time dilation, frame dragging effects, and the emission of gravitational waves that gradually reduce orbital energy and angular momentum. Understanding planetary and stellar motion reveals the hierarchical nature of cosmic structure, where smaller systems orbit within larger systems across scales ranging from planetary satellites to galaxy clusters. Each level of this hierarchy operates according to the same fundamental gravitational physics, but the resulting dynamics span enormous ranges of velocity, energy, and timescale that challenge human intuition and require sophisticated mathematical and computational tools for accurate description. The study of cosmic motion has practical applications for spacecraft navigation, asteroid hazard assessment, and the search for potentially habitable exoplanets around other stars. Understanding gravitational dynamics enables mission planners to design efficient trajectories that minimize fuel requirements and travel times, while gravitational microlensing techniques use stellar motion to detect and characterize planetary systems throughout the galaxy. As we transition from planetary and stellar motions to the most extreme velocities found in the universe, we encounter phenomena where matter accelerates to significant fractions of light speed through processes that involve the most powerful energy sources known to astrophysics. These cosmic accelerators reveal the ultimate limits of velocity that natural processes can achieve within the constraints imposed by fundamental physical laws. The universe contains natural particle accelerators that dwarf any human-built machine, accelerating matter to velocities so extreme that the particles carry energies equivalent to baseballs thrown at major league speeds, despite being smaller than atomic nuclei. These cosmic phenomena operate at energy scales that push the fundamental limits of physics, creating conditions where space and time themselves become malleable and where the familiar concepts of matter and energy undergo radical transformations. Neutron stars represent the most extreme examples of stellar rotation in the known universe. These collapsed stellar cores, with masses exceeding the Sun compressed into spheres merely 20 kilometers in diameter, spin at rates that challenge the structural limits of matter itself. The fastest known pulsar, designated PSRJ 1748-2446 AD and located in the globular cluster Terzan 5, rotates 716 times per second, creating surface velocities that approach 24% of light speed. The physics underlying neutron star formation involves gravitational collapse beyond the point where electron degeneracy pressure can support stellar structure against gravitational compression. When stars exceeding approximately 8 solar masses exhaust their nuclear fuel, core temperatures become insufficient to maintain thermal pressure against gravitational attraction. The resulting core collapse occurs over milliseconds, compressing matter to nuclear density where protons and electrons combine to form neutrons through inverse beta decay processes. The mathematical description of neutron star structure requires solving Einstein's field equations for general relativity, coupled with equations of state describing matter behavior under extreme density and pressure conditions. The Tolman-Oppenheimer-Volkoff equations generalize hydrostatic equilibrium to relativistic conditions, accounting for gravitational effects that become significant when escape velocities approach substantial fractions of light speed. These equations predict maximum masses for neutron stars of approximately 2 to 3 solar masses, above which gravitational collapse continues to form black holes. Conservation of angular momentum during stellar collapse explains the rapid rotation of newly formed neutron stars. If a slowly rotating star with radius comparable to the Sun collapses to neutron star dimensions, angular momentum conservation requires the rotation rate to increase by factors exceeding 10 to the fourth power. This amplification process transforms stars with rotation periods measured in weeks into millisecond pulsars spinning faster than kitchen blenders. The extreme rotation rates of millisecond pulsars create centrifugal forces that approach the gravitational binding forces holding the neutron star together. The mathematical condition for rotational stability requires that gravitational acceleration exceeds centrifugal acceleration at the stellar surface, leading to maximum rotation frequencies that depend on stellar mass and radius through relationships derived from general relativistic calculations. For typical neutron star parameters, this stability limit corresponds to rotation periods of approximately 1/2 millisecond. Pulsar magnetospheres represent some of the most extreme electromagnetic environments in the universe, with magnetic field strengths exceeding Earth's field by factors of 10 to the 12th power or more. These intense magnetic fields, generated by dynamo processes during neutron star formation and maintained by stellar rotation, create rotating electromagnetic structures that accelerate charged particles to relativistic velocities. The mathematical description of pulsar magnetospheres involves solving Maxwell's equations in curved spacetime, accounting for both general relativistic effects and plasma physics processes. Charged particles in pulsar magnetospheres follow magnetic field lines that corrotate with the neutron star, out to distances where the corrotation velocity would equal light speed. This light cylinder defines a critical boundary beyond which the rotating magnetic field structure becomes unstable, and particles escape as electromagnetic radiation and relativistic particle beams. The radius of the light cylinder equals the speed of light divided by angular velocity, typically extending hundreds to thousands of kilometers from the neutron star surface. The acceleration of particles within pulsar magnetospheres occurs through several physical mechanisms, including electric fields parallel to magnetic field lines and magnetic reconnection events where field topology changes rapidly. These processes can accelerate electrons and positrons to Lorentz factors exceeding 10 to the 6th power, corresponding to kinetic energies that approach the rest mass energy of protons. The mathematical description of particle acceleration in pulsar magnetospheres requires relativistic plasma physics calculations that account for radiation reaction forces and pair production processes. Cosmic rays represent the highest energy particles ever observed in nature, with energies that exceed 10 to the 20th power electron volts for the most extreme events. These ultra-high energy particles carry kinetic energies comparable to macroscopic objects, demonstrating that natural processes can concentrate enormous amounts of energy into individual subatomic particles through mechanisms that remain incompletely understood despite decades of intensive research. The detection of ultra-high energy cosmic rays requires extensive air shower arrays that monitor the cascade of secondary particles produced when primary cosmic rays interact with atmospheric nuclei. The Pierre Auger Observatory in Argentina covers over 3,000 square kilometers with detector stations that measure the lateral distribution and temporal structure of air shower particles. The mathematical reconstruction of primary particle energy and arrival direction from air shower data involves Monte Carlo simulations of hadronic interactions and electromagnetic cascades in the atmosphere. The energy spectrum of cosmic rays follows a power law distribution where particle flux decreases rapidly with increasing energy, creating natural selection effects that make the highest energy events extremely rare. The differential energy spectrum can be approximated as flux proportional to energy raised to the power negative gamma, where gamma approximately equals 2.7 for energies below the so-called Ni, at approximately 3 times 10 to the 15th power electron volts. Above this energy, the spectral index steepens, suggesting changes in acceleration mechanisms or propagation effects. The propagation of ultra-high energy cosmic rays through intergalactic space encounters fundamental limitations imposed by interactions with cosmic microwave background radiation. The Greisen-Zatsepin-Kuzmin cutoff predicts that protons with energies exceeding approximately 6 times 10 to the 19th power electron volts will lose energy through photopion production when colliding with microwave background photons. This energy threshold creates an effective horizon for ultra-high energy cosmic ray propagation, limiting detectable particles to sources within approximately 50 megaparsecs. Supernova remnants provide natural laboratories for studying cosmic ray acceleration through diffusive shock acceleration processes. When supernova explosions create expanding shock waves in the interstellar medium, charged particles can gain energy by repeatedly crossing the shock front, with each crossing providing incremental energy increases. The mathematical description of shock acceleration involves solving diffusion equations for particle transport in turbulent magnetic fields, coupled with hydrodynamic equations describing shock wave propagation through inhomogeneous media. The efficiency of shock acceleration depends on magnetic field turbulence levels, shock compression ratios, and particle injection mechanisms that determine which particles enter the acceleration process. For strong shocks with compression ratios approaching 4, the theoretical maximum efficiency approaches 10% of the shock kinetic energy, sufficient to accelerate particles to energies exceeding 10 to the 15th power electron volts under favorable conditions. However, achieving the highest observed cosmic ray energies may require more exotic acceleration mechanisms involving rotating black holes or other relativistic astrophysical objects. Active galactic nuclei powered by supermassive black holes represent potential sources of ultra-high energy cosmic rays through processes that remain theoretically challenging to understand. The accretion of matter onto black holes with masses exceeding millions of solar masses can release gravitational potential energy equivalent to rest mass energy through Einstein's mass-energy equivalence relationship E=mc². This energy release can power relativistic jets that extend thousands of light years from the central black hole, creating environments where particle acceleration to extreme energies becomes theoretically possible. The mathematical modeling of black hole jet formation requires general relativistic magnetohydrodynamics calculations that account for frame dragging effects near rotating black holes, magnetic field amplification through differential rotation, and the extraction of rotational energy through the Blanford's-Najdorf mechanism. These processes can generate Poynting flux exceeding 10 to the 45th power watts, providing sufficient power to accelerate cosmic rays to the highest observed energies if even a small fraction of the jet energy transfers to particle kinetic energy. Blazars, a subclass of active galactic nuclei with relativistic jets pointed toward Earth, demonstrate particle acceleration to extreme velocities through observations of rapid variability in gamma-ray emission. The shortest observed variability timescales of minutes to hours require emission regions smaller than light hours in size, yet these compact regions produce luminosities exceeding 10 to the 46th power watts. The combination of small size and enormous power output demands relativistic beaming effects, where particles move toward observers at velocities exceeding 99% of light speed. The Doppler boosting of radiation from relativistic jets amplifies observed luminosities and shortens observed variability timescales through relativistic effects described by the Doppler formula for moving sources. When particles move toward observers at velocities characterized by Lorentz factors gamma, the observed luminosity increases by factors of gamma to the fourth power for isotropic emission, while variability timescales decrease by factors of gamma. These effects explain how compact emission regions can produce the extreme luminosities observed from distant blazars. Magnetars, neutron stars with magnetic field strengths exceeding 10 to the 15th power Gauss, represent the most magnetically intense objects known in the universe. These extreme magnetic fields store energy densities that exceed nuclear binding energy, creating conditions where quantum electrodynamic effects become important and where magnetic pressure dominates both gravitational and nuclear forces. The mathematical description of magnetar physics requires quantum field theory calculations in strong magnetic fields, where vacuum polarization and magnetic Compton scattering modify electromagnetic interactions. The decay of magnetic fields through resistive dissipation and magnetic reconnection events releases enormous amounts of energy that can power explosive events called magnetar flares. The largest observed magnetar flare, detected from SGR 1806-20 in December 2004, released approximately 10 to the 46th power joules of energy in less than 1 second, equivalent to the total energy output of the Sun over 150,000 years. This energy release demonstrates the enormous reservoir of magnetic energy stored within magnetar magnetic field structures. Gamma-ray bursts represent the most energetic electromagnetic events known in the universe, releasing energies exceeding 10 to the 44th power joules in timescales ranging from milliseconds to thousands of seconds. The mathematical modeling of gamma-ray burst emission requires understanding relativistic shock waves, magnetic field amplification, and particle acceleration in environments characterized by Lorentz factors exceeding 100. The observed isotropy of gamma-ray burst distribution suggests cosmological distances, making these events visible across significant fractions of the observable universe. Long-duration gamma-ray bursts appear to result from the collapse of massive stars into black holes, creating conditions where relativistic jets can break through stellar envelopes and accelerate particles to extreme energies. The mathematical description of this process involves general relativistic hydrodynamics calculations that follow jet propagation through stellar density profiles, accounting for energy losses due to baryon loading and radiative cooling. Successful jet breakout requires sufficient energy input to overcome stellar binding energy and create the relativistic expansion necessary for gamma-ray production. Short-duration gamma-ray bursts likely result from neutron-star mergers, events that create kilonova explosions and generate gravitational waves detectable by laser interferometer facilities. The simultaneous detection of gravitational waves and gamma-ray emission from GW 170817 in August 2017 provided direct confirmation of the neutron-star merger model for short gamma-ray bursts. This observation demonstrated how compact object mergers can accelerate particles to relativistic velocities while producing both electromagnetic and gravitational wave signatures. The study of extreme astrophysical phenomena reveals fundamental connections between gravity, electromagnetism, and quantum mechanics under conditions that cannot be replicated in terrestrial laboratories. These cosmic laboratories enable tests of physical theories at energy scales and field strengths that approach the Planck scale, where quantum gravitational effects may become important. Understanding particle acceleration in these environments provides insights into fundamental physics that complement particle accelerator experiments and theoretical investigations. The highest energy cosmic rays challenge our understanding of both acceleration mechanisms and particle propagation through intergalactic space. The mathematical modeling of these phenomena requires interdisciplinary approaches that combine astrophysics, particle physics, and cosmology to create coherent theoretical frameworks capable of explaining observations that span energy scales from laboratory experiments to the most extreme natural processes in the universe. As we transition from stellar-scale particle accelerators to the fundamental speed limit of the universe, we encounter the ultimate constraint that governs all motion, the speed of light in vacuum. This cosmic speed limit emerges not as an arbitrary restriction, but as a fundamental property of space-time geometry itself, revealing deep connections between space, time, energy, and information that transform our understanding of physical reality. Chapter 7. The Light Limit, Nature's Speed Ceiling. The speed of light stands as the universe's ultimate speed limit, not through some arbitrary cosmic regulation, but as a fundamental property woven into the very fabric of space-time itself. This limiting velocity of 299,792,458 meters per second represents far more than a mere measurement. It embodies the deep mathematical structure that connects space, time, energy, and matter in ways that revolutionized physics and continue to challenge human intuition about the nature of reality. Einstein's special theory of relativity, published in 1905, demonstrated that the speed of light in vacuum remains constant for all observers regardless of their motion or the motion of light sources. This seemingly simple postulate leads to profound consequences that overturn centuries of intuitive understanding about absolute space and time. The mathematical framework of special relativity shows that space and time form a unified four-dimensional continuum, where the speed of light serves as the fundamental conversion factor between spatial and temporal measurements. The invariance of light speed arises from the electromagnetic nature of light itself and the structure of Maxwell's equations governing electromagnetic phenomena. These equations predict that electromagnetic waves propagate at a velocity equal to 1 divided by the square root of permittivity times permeability of free space. This velocity emerges as a fundamental constant of nature, independent of reference frame motion, because the electromagnetic properties of vacuum remain unchanged by coordinate transformations. The Lorentz transformation equations describe how measurements of space and time intervals change between reference frames, moving at constant velocities relative to each other. These transformations involve the Lorentz factor gamma, calculated as 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. As relative velocities approach light speed, this factor approaches infinity, indicating that infinite energy would be required to accelerate massive objects to light speed. Time dilation represents one of the most counterintuitive consequences of special relativity, where moving clocks run slower as measured by stationary observers. The mathematical relationship shows that proper time intervals measured by moving observers equals coordinate time intervals divided by the Lorentz factor. This effect becomes significant only at velocities approaching substantial fractions of light speed, explaining why relativistic effects remain imperceptible in everyday experience. Experimental verification of time dilation has been confirmed through numerous high-precision measurements using atomic clocks, particle decay rates, and astronomical observations. The global positioning system requires relativistic corrections to maintain accuracy, accounting for both special relativistic effects due to satellite motion and general relativistic effects due to gravitational time dilation in Earth's gravitational field. Without these corrections, GPS accuracy would degrade by several kilometers within hours. Length contraction provides another manifestation of relativistic effects, where objects appear shortened along their direction of motion as observed from stationary reference frames. The contracted length equals the proper length times the square root of 1 minus velocity squared divided by the speed of light squared. This effect, combined with time dilation, ensures that all observers measure the same speed of light despite their relative motion. The relativistic velocity addition formula demonstrates how velocities combine in special relativity, differing significantly from classical expectations at high speeds. When two velocities u and v are added relativistically, the result equals u plus v divided by 1 plus uv divided by the speed of light squared. This formula ensures that no combination of velocities can exceed light speed, maintaining the universal speed limit regardless of reference frame motion. Mass-energy equivalence, expressed through Einstein's famous equation E equals mc squared, reveals that mass and energy represent different aspects of a single physical quantity. This relationship shows that rest mass energy equals rest mass times the speed of light squared, demonstrating that the speed of light serves as the fundamental conversion factor between mass and energy units. The enormous magnitude of this conversion factor explains why even small amounts of matter correspond to tremendous energy quantities. The relativistic energy-momentum relationship generalizes mass-energy equivalence to moving objects, showing that total energy squared equals rest mass energy squared plus momentum squared times the speed of light squared. For massless particles like photons, rest mass energy equals 0, so total energy equals momentum times the speed of light. This relationship explains how massless particles can carry energy and momentum while traveling at exactly light speed. Photons, the quantum particles of electromagnetic radiation, always travel at light speed in vacuum and cannot be slowed down or accelerated through any physical process. The energy of individual photons equals Planck's constant times frequency, while their momentum equals energy divided by the speed of light. These relationships connect the wave and particle descriptions of light through fundamental constants that characterize the quantum nature of electromagnetic radiation. The electromagnetic spectrum spans enormous frequency ranges, from radio waves with frequencies below 1 Hz to gamma rays with frequencies exceeding 10 to the 24th power Hertz. Despite this vast range of photon energies, all electromagnetic radiation propagates at exactly the same speed in vacuum, demonstrating the universal nature of the light speed limit for massless particles. Gravitational waves, predicted by Einstein's general theory of relativity and first directly detected by LIGO in 2015, also propagate at exactly light speed. These ripples in space-time itself result from accelerated motion of massive objects, particularly in extreme astrophysical environments like merging black holes and neutron stars. The detection of gravitational waves traveling at light speed confirmed a fundamental prediction of general relativity and opened new observational windows into high-energy astrophysical phenomena. The mathematical description of gravitational waves involves linearized general relativity, where small perturbations in space-time metric components satisfy wave equations similar to Maxwell's equations for electromagnetic waves. The amplitude of gravitational waves decreases as one over distance from their sources, making detection extremely challenging and requiring unprecedented precision in laser interferometer measurements. Neutrinos provide interesting tests of the light speed limit because these nearly massless particles travel at velocities extremely close to, but slightly less than, light speed. Neutrino velocity measurements require precise timing of particle detection over astronomical distances, using sources like supernovae where neutrinos and photons are produced simultaneously through different physical processes. The small but measurable time delays between neutrino and photon arrival confirm that neutrinos have finite rest mass and travel slower than light. The mathematical relationship between neutrino velocity and mass involves the relativistic energy-momentum formula, where neutrino velocity equals momentum divided by energy times the speed of light. For ultra-relativistic neutrinos with kinetic energy much greater than rest mass energy, the velocity approaches light speed but remains slightly less due to the finite rest mass contribution to the total energy. Cherenkov radiation demonstrates interesting consequences of the light speed limit in material media, where the speed of light becomes reduced below its vacuum value due to interactions with matter. When charged particles move through transparent media at velocities exceeding the local light speed, they emit Cherenkov radiation as a shockwave phenomenon analogous to sonic booms for supersonic aircraft. This blue glow, observed in nuclear reactor cooling pools and cosmic ray air showers, provides direct evidence for relativistic particle motion. The refractive index of materials determines the reduced light speed through the relationship where light velocity in the medium equals the vacuum light speed divided by the refractive index. This reduction occurs because electromagnetic waves interact with atomic and molecular electric dipoles in the material, creating oscillating currents that modify the effective electromagnetic properties of the medium. Dispersion effects in optical materials cause different wavelengths of light to travel at slightly different velocities, leading to phenomena like rainbow formation in prisms and chromatic aberration in optical systems. The mathematical description of dispersion involves frequency-dependent refractive indices that follow empirical relationships like the Cauchy equation or more sophisticated models based on atomic and molecular physics. Group velocity and phase velocity provide different measures of wave propagation that can differ significantly in dispersive media. Group velocity describes the speed at which wave packets or pulses propagate, while phase velocity characterizes the motion of constant phase surfaces. In some materials, group velocity can exceed the vacuum speed of light or even become negative, but these phenomena do not violate relativistic causality because information and energy still propagate at subluminal speeds. Quantum field theory provides the mathematical framework for understanding why light speed represents a fundamental limit rather than merely a practical constraint. The structure of Minkowski spacetime, with its signature of 3 spatial dimensions and 1 time dimension, naturally incorporates the light speed limit through the spacetime interval that remains invariant under Lorentz transformations. This geometric approach shows that the speed of light emerges from the fundamental structure of spacetime itself. The principle of relativity requires that physical laws maintain the same mathematical form in all inertial reference frames, a requirement that severely constrains the possible structure of fundamental physical theories. Maxwell's equations automatically satisfy this requirement when combined with Lorentz transformations, explaining why electromagnetic theory naturally incorporates special relativistic effects, even though these were not recognized when the equations were originally formulated. Tachyons represent hypothetical particles that would travel faster than light if they existed, but their properties would violate causality and create logical paradoxes in relativistic physics. The mathematical description of tachyons requires imaginary rest mass values that lead to complex energy relationships and unstable vacuum states. Most physicists consider tachyons to be mathematical curiosities rather than physical possibilities because their existence would undermine the logical consistency of relativistic theories. The search for violations of Lorentz invariance represents an active area of experimental physics, where researchers use high-precision measurements to test whether the fundamental symmetries of special relativity remain exact under all conditions. These tests include comparisons of atomic clock rates, measurements of particle velocities at different energies, and studies of electromagnetic wave propagation through space. All measurements to date confirm Lorentz invariance to extraordinary precision, supporting the fundamental nature of the light speed limit. The cosmological constant problem in quantum field theory arises partly from attempts to understand why virtual particle fluctuations in the quantum vacuum do not create observable violations of special relativity. The mathematical calculation of vacuum energy density using quantum field theory techniques yields results that exceed observational limits by factors of 10 to the 120th power, suggesting fundamental gaps in our understanding of how quantum mechanics and relativity connect at the deepest levels. String theory attempts to unify quantum mechanics and general relativity through mathematical frameworks where fundamental particles appear as vibrational modes of one-dimensional strings rather than point particles. These theories naturally incorporate the light speed limit through their geometric structure, but they require additional spatial dimensions beyond the familiar 3 dimensions of everyday experience. The mathematical consistency of string theories depends critically on maintaining Lorentz invariance and the associated light speed limit. Experimental tests of special relativity continue to push the boundaries of measurement precision, using techniques like laser interferometry, atomic spectroscopy, and particle accelerator studies to probe potential deviations from relativistic predictions. The most stringent tests of the light speed limit involve comparisons of electromagnetic and gravitational wave propagation, measurements of particle velocities at extreme energies, and searches for directional variations in fundamental constants that might indicate preferred reference frames. The Kennedy-Thorndike experiment and its modern variants test whether the speed of light depends on the velocity of Earth through space by comparing the frequencies of orthogonal laser cavities as Earth's orbital motion changes direction. These experiments have confirmed the isotropy of light speed to parts per 10 to the 17th power, demonstrating that no preferred reference frame exists for electromagnetic propagation. Particle accelerator experiments provide direct tests of relativistic energy-momentum relationships by accelerating particles to velocities exceeding 99.9999% of light speed. The measured relationship between particle energy, momentum, and velocity precisely follows relativistic predictions, confirming that no massive particle can reach or exceed light speed, regardless of the energy supplied to the acceleration process. The light speed limit emerges as a fundamental organizing principle that connects diverse areas of physics through mathematical relationships that would otherwise appear unrelated. Thermodynamic irreversibility, electromagnetic wave propagation, quantum mechanical uncertainty principles and gravitational field equations all incorporate the speed of light in ways that reflect its role as a fundamental property of space-time geometry rather than merely a property of electromagnetic phenomena. Information theory provides another perspective on the light speed limit through considerations of causal relationships and the maximum rate at which information can propagate between spatially separated events. The no-communication theorem of quantum mechanics shows that quantum entanglement cannot be used to transmit information faster than light, maintaining consistency between quantum mechanics and special relativity despite the seemingly instantaneous correlations observed in entangled particle measurements. The holographic principle in theoretical physics suggests that all information contained within a volume of space can be encoded on its boundary surface, with the encoding density limited by the Planck scale and the light speed propagation of information. This principle connects the light speed limit to fundamental questions about the nature of information, entropy, and the microscopic structure of space-time at the smallest possible scales. As we approach the final frontier of speed, we encounter phenomena that seem to transcend even the light speed limit while remaining consistent with relativistic physics. These apparent violations reveal subtle distinctions between different concepts of velocity and demonstrate how the expansion of space itself can create motion faster than light without contradicting the fundamental principles that establish the cosmic speed limit. The ultimate frontier of velocity extends beyond individual particle motion to encompass the expansion of space itself, where the very fabric of reality stretches at rates that dwarf light speed without violating any physical laws. This cosmic expansion reveals that the universe possesses mechanisms for achieving superluminal motion through processes fundamentally different from ordinary particle acceleration, opening possibilities for understanding motion on scales that transcend even the light speed barrier. Cosmological expansion, first discovered through observations of distant galaxy redshifts by Edwin Hubble in the 1920s, demonstrates that space itself grows continuously, carrying galaxies away from each other at velocities proportional to their separation distances. The Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec, quantifies this expansion rate and reveals that galaxies separated by sufficiently large distances recede from us faster than light speed. The mathematical description of cosmological expansion uses the Friedmann equations derived from Einstein's general relativity applied to homogeneous isotropic universe models. These equations relate the expansion rate to the energy density and pressure of matter and radiation filling space, showing how cosmic expansion results from the gravitational effects of the universe's total energy content rather than from explosive motion through pre-existing space. The crucial distinction between recession velocity and motion through space resolves the apparent contradiction between superluminal recession and the light speed limit. Galaxies do not move through space faster than light. Instead, the space between them expands, creating increasing separation distances that change at rates exceeding light speed for sufficiently distant objects. This expansion occurs everywhere simultaneously, stretching the metric of space-time itself, rather than moving objects through a fixed spatial background. The observable universe's radius currently extends approximately 46 billion light-years, despite the universe's age of only 13.8 billion years. This apparent paradox resolves when accounting for cosmic expansion during the light travel time from distant objects. Photons emitted from the cosmic microwave background have traveled for nearly the universe's entire lifetime, but the sources of this radiation have moved much farther away due to continued expansion during the photon journey. Cosmic inflation represents an even more extreme example of superluminal expansion, where the early universe underwent exponential expansion that stretched space by factors exceeding 10 to the 26th power in less than 10 to the negative 32 seconds. During inflation, regions of space separated by subatomic distances expanded to sizes exceeding the current observable universe, with expansion velocities that exceeded light speed by enormous factors. The physics of cosmic inflation involves scalar fields with unusual equation of state properties, where pressure becomes negative and approximately equal in magnitude to energy density. This creates a gravitational effect that drives accelerated expansion rather than the decelerated expansion expected from ordinary matter and radiation. The mathematical description of inflation uses field theory techniques similar to those describing fundamental particle interactions, but applied to cosmological scales. Eternal inflation models suggest that the inflationary process continues indefinitely in most regions of space, with occasional transitions to slower expansion rates that create observable universes like our own. These models predict a multiverse structure, where countless bubble universes form within an eternally expanding inflationary background, each potentially having different physical laws and constants determined by random quantum fluctuations during their formation. The horizon problem in cosmology illustrates how superluminal expansion provides solutions to otherwise puzzling observations. The cosmic microwave background radiation exhibits nearly identical temperatures in opposite directions on the sky, despite these regions being separated by distances that exceed the light travel distance since the Big Bang. Inflation resolves this puzzle by showing that apparently disconnected regions were actually in causal contact before undergoing superluminal expansion. Dark energy, which currently drives accelerated cosmic expansion, represents approximately 68% of the universe's total energy content. This mysterious component causes expansion to accelerate rather than decelerate, leading to exponentially increasing distances between galaxy clusters over cosmic time. The mathematical description of dark energy often involves Einstein's cosmological constant, but alternative theories propose dynamic scalar fields or modifications to general relativity on cosmological scales. The ultimate fate of cosmic expansion depends on the nature of dark energy and its evolution over time. If dark energy density remains constant, the universe will undergo exponential expansion that eventually separates all gravitationally unbound structures by distances exceeding the observable horizon. In this scenario, future observers would see only their local galaxy group, with all other structures receding beyond the cosmic horizon at superluminal speeds. Theoretical proposals for faster-than-light travel exploit loopholes in special relativity that allow superluminal motion without violating fundamental physical principles. The Alcubierre warp drive concept involves contracting space in front of a spacecraft while expanding space behind it, creating a warp bubble that carries the vehicle faster than light relative to distant observers, while keeping it stationary relative to local spacetime. The mathematical description of the Alcubierre drive requires exotic matter with negative energy density to create the necessary spacetime curvature for superluminal travel. The energy requirements for such devices exceed the mass energy of observable matter by enormous factors, making practical implementation impossible with known physics. However, recent theoretical developments suggest that modified designs might reduce energy requirements to more reasonable levels. Quantum entanglement creates correlations between spatially separated particles that appear to involve instantaneous communication. But detailed analysis shows that no information actually propagates faster than light during entanglement measurements. The mathematical formalism of quantum mechanics describes these correlations through wave-function collapse that occurs simultaneously in all reference frames, but the randomness of measurement outcomes prevents superluminal information transmission. The EPR paradox, formulated by Einstein, Podolsky and Rosen in 1935, challenged the completeness of quantum mechanics by arguing that quantum entanglement required either superluminal communication or hidden variable theories. Bell's theorem and subsequent experiments have ruled out local hidden variable explanations, confirming that quantum mechanics correctly describes nature despite its counterintuitive implications for the relationship between measurement and reality. Wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe, offer another theoretical possibility for effective, faster-than-light travel. The mathematical description of wormholes uses solutions to Einstein's field equations that create topology changes in space-time, allowing shortcuts between regions that would otherwise require superluminal speeds for direct travel through normal space. Traversable wormholes require exotic matter with negative energy density to prevent their collapse, similar to the requirements for Alcubierre drives. The mathematical analysis of wormhole stability involves understanding quantum field theory in curved space-time, where virtual particle effects and Hawking radiation may destabilize wormhole structures before they can be traversed by macroscopic objects. Closed time-like curves, mathematical solutions to general relativity that allow travel backward in time, raise fundamental questions about causality and the consistency of physical laws. These solutions often require exotic matter distributions or extreme gravitational fields that may not exist in realistic astrophysical environments. The chronology protection conjecture suggests that quantum effects prevent the formation of closed time-like curves, maintaining causal consistency. Extra-dimensional theories propose that space contains additional spatial dimensions beyond the familiar three dimensions of everyday experience. In these theories, fundamental particles might propagate through higher dimensional space while being confined to three-dimensional branes, potentially allowing shortcuts through extra dimensions that could enable effective faster-than-light travel within three-dimensional space. The mathematical description of extra-dimensional theories involves generalizing Einstein's field equations to higher dimensional spacetimes, with additional geometric structures that determine how matter and energy distribute across the extra dimensions. String theory provides the most developed framework for understanding physics in higher dimensional spaces. But experimental verification remains challenging due to the extremely small scales at which extra dimensions are expected to manifest. Quantum tunneling of composite objects represents another theoretical possibility for superluminal motion, where macroscopic objects could tunnel through potential barriers faster than light could traverse the same distance through normal space. However, the mathematical analysis of macroscopic quantum tunneling shows that tunneling times become independent of barrier width for sufficiently thick barriers, preventing genuine superluminal information transfer. The group velocity of electromagnetic wave packets in dispersive media can exceed the vacuum speed of light under certain conditions, leading to pulse propagation that appears superluminal. However, detailed analysis shows that the peak of such pulses can exit the medium before the entire pulse has entered, demonstrating that superluminal group velocity does not enable faster-than-light information transmission. Recent theoretical developments in quantum field theory and condensed matter physics have revealed phenomena like quantum phase transitions and topological insulators that exhibit properties reminiscent of space-time physics. These analogies suggest that laboratory condensed matter systems might provide controllable environments for studying phenomena similar to cosmological expansion, black hole physics, and even aspects of quantum gravity. The mathematical connections between condensed matter physics and cosmology involve similar field theoretical techniques applied to different physical systems. Quantum phase transitions in condensed matter exhibit critical phenomena analogous to phase transitions in the early universe, while topological insulators display surface states that resemble the holographic principle in quantum gravity theories. Understanding superluminal phenomena requires careful attention to the distinction between different types of velocity and the information content of various physical processes. While space itself can expand faster than light, and various wave phenomena can exhibit superluminal group velocities, the fundamental principle that information cannot propagate faster than light remains inviolate and provides the ultimate constraint on causal relationships in physics. The study of superluminal phenomena has revealed deep connections between seemingly unrelated areas of physics, from cosmology and quantum mechanics to condensed matter and high-energy particle physics. These connections suggest underlying unifying principles that transcend traditional disciplinary boundaries and point toward more complete theories of quantum gravity and the fundamental structure of space-time. Our journey through the universe's extremes of motion reveals a profound truth that transcends the individual phenomena we have explored. The same fundamental principles that govern quantum stillness at absolute zero also determine cosmic expansion beyond the observable horizon. This unity represents one of physics' most remarkable discoveries, that nature operates according to mathematical laws of extraordinary elegance and generality that connect the smallest and largest scales of existence through relationships of stunning beauty and precision. The mathematical framework underlying this unity centers on conservation principles and symmetries that remain invariant across all scales of space and time. Energy conservation connects the thermal motion of atoms approaching absolute zero to the kinetic energy of galaxies racing away from us at cosmic velocities. Momentum conservation links bacterial flagella motors to the orbital dynamics of binary pulsars. Angular momentum conservation explains both the formation of millisecond pulsars and the rotation curves of spiral galaxies that revealed dark matter's existence. These conservation laws emerge from fundamental symmetries in the mathematical structure of physical theories. Noether's theorem demonstrates that every continuous symmetry corresponds to a conserved quantity, revealing why conservation principles appear universal, regardless of the specific physical systems involved. Time translation symmetry generates energy conservation, spatial translation symmetry creates momentum conservation, and rotational symmetry produces angular momentum conservation across all scales from quantum mechanics to cosmology. The speed of light serves as the fundamental constant that unifies our understanding of space, time, energy and matter across the entire range of phenomena we have explored. This cosmic speed limit determines the thermal motion of atoms through the fine structure constant, governs electromagnetic radiation from pulsars through Maxwell's equations, and constrains cosmic expansion through general relativity. The universality of this limit demonstrates that local physics experiments can reveal fundamental truths about the nature of space and time on cosmic scales. Scale invariance and self-similarity appear repeatedly throughout our exploration, suggesting deep organizational principles that transcend specific physical mechanisms. The power law distributions that characterize everything from molecular velocity distributions to galaxy clustering patterns reflect underlying statistical and dynamical processes that operate similarly across vastly different scales. These scaling relationships provide predictive frameworks that enable extrapolation from laboratory measurements to astrophysical phenomena and vice versa. Quantum mechanics provides the underlying mathematical structure that connects discrete atomic behavior to continuous macroscopic phenomena through statistical mechanics and thermodynamic limit procedures. The quantum mechanical origin of thermal motion at absolute zero connects directly to the quantum vacuum fluctuations that may drive cosmic inflation, demonstrating how quantum effects influence physics from subatomic to cosmological scales through mechanisms that remain fundamentally quantum mechanical despite their macroscopic manifestations. The geometric nature of space-time, revealed through Einstein's relativity theories, shows that motion and gravity represent different aspects of space-time curvature rather than separate physical phenomena. This geometric insight unifies diverse observations from GPS satellite corrections to black hole event horizons, revealing that the same mathematical structures govern both everyday navigation and the most extreme astrophysical environments. Information theory provides another unifying perspective that connects thermodynamic entropy to black hole entropy, quantum entanglement to cosmological horizons, and biological evolution to cosmic structure formation. The mathematical relationships describing information processing and transmission operate similarly across biological, technological, and physical systems, suggesting fundamental connections between computation, complexity, and physical law. The hierarchy of characteristic velocities we have explored reflects the energy scales at which different physical processes operate. Thermal velocities depend on temperature through kinetic theory. Escape velocities depend on gravitational binding energy. And relativistic velocities approach fundamental limits determined by rest mass energy. These relationships reveal how energy and velocity interconnect through mathematical structures that span the entire range of physical phenomena. Feedback mechanisms and control systems appear at every level of our exploration, from quantum measurement processes to biological locomotion to cosmic structure formation. The mathematical description of these control systems involves similar differential equations and stability criteria, regardless of whether they govern molecular motors, animal nervous systems, or galactic dynamics. This universality suggests that control and regulation represent fundamental aspects of physical law rather than emergent properties of complex systems. The role of randomness and deterministic chaos appears throughout our journey, from quantum uncertainty at absolute zero to turbulent flows in stellar atmospheres to the apparent randomness in cosmic ray arrival directions. The mathematical tools for understanding these phenomena, including statistical mechanics, nonlinear dynamics, and information theory, provide unified frameworks for analyzing seemingly random behavior that emerges from deterministic underlying laws. Optimization principles appear repeatedly across all scales, from the minimum action principles that govern fundamental particle interactions to the evolutionary optimization of biological locomotion to the geodesic principles that determine planetary orbits. These optimization principles reflect deep mathematical structures that minimize certain quantities, suggesting that nature operates according to variational principles that transcend specific physical mechanisms. The emergence of complexity from simple rules manifests across our entire exploration, from the complex behavior of gases approaching absolute zero, to the intricate dynamics of biological systems, to the large-scale structure of the universe. The mathematical understanding of emergence involves concepts from statistical mechanics, information theory, and complexity science that reveal how macroscopic properties can differ qualitatively from microscopic behavior while remaining ultimately derivable from fundamental laws. Our exploration reveals that the concept of motion itself undergoes profound changes as we progress through different scales and regimes. At quantum scales, motion becomes probabilistic and subject to uncertainty principles. At relativistic scales, motion affects the flow of time and the structure of space. At cosmological scales, motion becomes inseparable from the expansion of space itself. These transformations in the meaning of motion reflect deeper changes in the mathematical frameworks required to describe physical phenomena at different scales. The practical applications emerging from this unified understanding continue to transform human technology and capabilities. Quantum technologies exploit the connection between thermal motion and quantum coherence. GPS navigation requires understanding both special and general relativity. Medical imaging uses principles from nuclear physics and quantum mechanics. Climate modeling integrates processes operating from molecular to planetary scales. Space exploration demands understanding of gravitational dynamics, plasma physics, and relativistic effects. The philosophical implications of this unity challenge traditional boundaries between different scientific disciplines and suggest that the universe possesses an underlying mathematical structure of remarkable coherence and beauty. The fact that human minds can discover and understand these universal principles raises profound questions about the relationship between consciousness, mathematics, and physical reality that continue to inspire both scientific research and philosophical reflection. Future discoveries will likely reveal even deeper connections between phenomena that currently appear unrelated, extending the unifying principles we have explored to new domains of physics and possibly to new scales of space and time beyond our current observational capabilities. The mathematical frameworks that successfully describe known phenomena provide strong foundations for understanding whatever new discoveries await in humanity's continued exploration of the universe's extremes. The journey from stillness to light speed ultimately reveals that motion and rest, fast and slow, near and far, represent different aspects of a single unified reality governed by mathematical principles of extraordinary elegance and power. Understanding these principles provides not merely intellectual satisfaction, but practical tools for continuing humanity's exploration of the cosmos and our place within it. This exploration demonstrates that science's greatest triumph lies not in cataloguing isolated phenomena, but in revealing the deep connections that unite apparently disparate aspects of reality. The speed of a quantum particle tunneling through a barrier at absolute zero connects mathematically to the recession velocity of distant galaxies, revealing a universe of profound unity disguised by its magnificent diversity of phenomena across the full spectrum of motion, from the universe's slowest to its fastest manifestations.